Hello all, I want to welcome you to today's lecture. Today we will be addressing the molecular geometry of molecule, and this is a sequel to the last lecture that we talked about Lewis structure. So molecular geometry simply means the 3D of molecules. That's exactly another way of looking at this topic. We're looking at the three-dimensional structure of molecules, and that's exactly what we're going to be doing today. Let's take it off from there immediately. I have a quote from Dalai Lama of Tibet. I'm not going to say anything about it. I'm just going to read it for you. It says, when you've realized you made a mistake, take immediate steps to correct it. So this is a food for thought. Let's take it off immediately. Now, in this lecture, I have just one learning objective to achieve. And what is that? It is, we're going to be using the VSEPR model. The VSEPR model is what we call the VSEPR model. Another way I can say it is the valence shell electron pair repulsion model to predict the shapes or molecular geometry or the 3D of molecules of covalent compounds. And that's just one objective that we're going to be addressing in this chapter. So molecular geometry or molecular shape of molecules. Now, VSEPR model simply means valence shell electron pair repulsion. It's a theory that is based on the mutual repulsion of electrons when they are in close proximity with with each other. Now, look at what this means is that, remember, if I have to just review this, that if an atom is bonded to an atom, just remember again that this bond just simply means a pair of electrons. So if I want to write this in another way, come to assembly, say that X is also bonded to another X. That's exactly another way you can put this in principle. However, now, atoms, when molecules form, of course, they are formed as a result of the sharing of these electrons. Remember, this simply means two electrons, like I just said here, or you can say a pair of electrons. So let me give you an example. Let me show you a very good image to do this. So if I have an atom this way, so the A's represent the two peripheral atoms, whereas the X is the central atom. And if the central atom has a lone pair, remember this lone, okay, let me use just the dot for now. I'm not going to use the dot, but it's something. The dot here represents an electron. What does it say? So I can always use this or this as I do this lecture. It doesn't really matter. They remain the same thing. All right? You can't use one dot. It has to be either two dots or a dash. Now, since we know that like terms repel, unlike terms attract, according to the Cardinal Henry's law, what it simply means is that I'm going to use a different color. Is that these electrons here, let's see, if I use a different color now, these are electrons, these are electrons. Since they're negatively charged, they're going to try to push each other away. And what that simply means is that if they push each other away, they will end up assuming a different shape. The shape of this molecule is going to finally become or look this way. Because this electron has so much power that it has pushed these other peripheral bonds away, the shape of this molecule will now look in a different way. So this becomes exactly what we mean by that valence shell electron pair repulsion. That these electrons will repel each other so that they are going to maximize this separation from each other. And that maximization of this distance is what gives the overall three-dimensional shape of molecules. And of course, this happens around the central atom. What is a central atom? Any atom that is bonded to two or more other atoms is what we call a central atom. And of course, just as a reminder, and this particular atom, of course, that is not bonded is called a what? A non-bonding pair. This non-bonding pair of electron is called a lone pair. It's called a lone pair. It's called a lone pair of electron, or LP of electron. And in fact, it is the lone pair that brings about a change in the two-dimensional name to the three-dimensional name of these molecules, as we're going to see as we move on. Okay, we go to the next thing. So how do we now apply the knowledge of this separation of electrons to figure out the three-dimensional shape of molecules? That is exactly what we're going to do next. Now, first thing first, all valence shell electron pairs are counted as equal. Every electron around the central atom are counted as equal, whether they are bonding between two atoms or whether they are non-bonding lone pairs. What does that mean? Okay, let me give you an example. So assuming again I have something like this, and I have A and A, and this atom has two lone pairs and another atoms attached around it. If I want to count the number of electron pairs around this or attachment, I'm going to count. Okay, I'm going to use my green. If I use my green, I'm going to count 1, 2, 3, 4. So I'm going to say there are 4 pairs of electrons or 4 attachments around this my hypothetical molecule. So I'm counting both the atoms and the lone pairs equally as the same. Secondly, what is another rule? The another rule is saying is that the double bonds and triple bonds are counted equally. It doesn't matter. Now, if an atom has a triple bond, or it has a double bond, or it has a single bond, they are all counted as a single pair of electrons. It does not matter how many bonds between them. And we're going to see the application of this. And one last thing is that the electron pair geometry name, which is what we call the EPG, some people will call it electron geometry or electron domain. So whichever one you want to call it, electron domain. So the electron domain name will only differ from the molecular geometry name or the three-dimensional name, only if the central atom has a lone pair. So we need to worry about only when this atom have a lone pair, because it is the lone pair that makes all the differences. The lone pair makes all the differences. So now there are 3 basic electron arrangements around atoms we're going to be looking at. First of all, if there are 2 atoms arranged, now assuming this is the central atom and it has 2 attachments, which could be a lone pair on atom, it will assume a linear shape. If there are 3 things attached around the central atom like this way, we have a central atom here and it has 3 attachments or 3 lone pairs around it. It's going to be looks like a triangle, and we call that a trigonal planar. Again, if there are 4 things attached around this atom, I drew this like a 3D. So if the 2D, well, look this way, let me put it this way. If I have something like this, 4 stuff attached around the central atom, it's going to assume a tetrahedral shape. And it is your responsibility to memorize these electron pair geometry and then the VSEPR 3-dimensional geometry. So this table is going to remain a guide, and it's your responsibility to memorize this table and understand how it works. Now, however, by the time we start solving our problems, we're going to get this thing particularly situated. Now, this first column represents the number of atoms that are attached. Now, this tells you the number of lone pair that are attached. Now, here I tried to add, I made this table. Here I added the total number of atoms at the lone pair. Then what is the electron geometry name? What it will look like. The electron geometry or electron pair, you can say electron pair EPG. This means the EPG name. And then this is the 2-dimensional nature. Now this is the molecular geometry name. This is what it will look like in this column. Now this is the bond angle, and this is a good example. So let's start. When you have only 2 atoms attached and there's no lone pair, what that simply tells you is that there are just 2 atoms, no lone pair. The electron geometry is going to be linear, because this is a good example. This is the central, oh, here I used A as a central. So this is the central atom, and this is X, this is X. What it means is that there are 2 atoms attached on both sides. So it's going to be a linear molecule like I just told you. The bond angle is going to be 180, and this is a good example, carbon dioxide. If there are 3 things attached around it, and there's no lone pair, just like this guy, it's going to be a trigonal planar. Now, this is not going to change because there's no lone pair. Now, this is the 3-dimensional nature. It's going to be the same thing. Again, if there are 4 things attached, like we said earlier, it's going to be tetrahedral. There are 4 things attached. Now, whenever there are 4 things attached, the 3-dimensional drawing will change, because there is one side you're not going to see. So look at this. This looks like a tetrahedron. Now, the dash here means that you cannot, this is pointing away from you or into the board, that you cannot see it. This one, the thick one, is coming to you, and this looks at the plane of your eye. You can see up and above, and then the bond angle is this, and then this is a good example. Now it begins to change. Look at this one now. This one now, there are a total of 3 attachments, but in those 3 attachments, one is a lone pair, 2 atoms. This is a good example. 1 lone pair, 2 atoms. Now because there are a total of 3 things attached, the electron geometry is going to be trigonal. So the electron geometry tells you the total number of attachments is both lone pairs and atoms. It's going to give you trigonal plane. However, because of this lone pair is going to push these bonds down to become a bent molecule. And this type of molecule, of course, because the EPG or the electron geometry is trigonal, is going to have a bond angle of this. If you go down to here, again, there are 4 attachments, 1 lone pair. Again, look at what we have here. 4 atoms, 1 lone pair. There are a total of 4 attachments. It's going to be tetrahedral. Because of this 1 lone pair here, it's going to push this bond down to look this way, and then it's going to become a trigonal pyramid. And then if there are also 2 atoms attached and 2 lone pair, we're going to have 4 total. The electron geometry has 4 total, give us a tetrahedral. Because of these 2 lone pairs on both sides, they're going to situate themselves this way, whereby that each of these guys will push this bond down, and this is also going to give us a bent shape, and it will also be a 109.5 degrees, because it has to be equal to, both of them are tetrahedral geometry, so the bond angle is determined. The bond angles are determined by the electron geometry and not by the molecular geometry. And a good example here is water. So we're going to try to see this and then practice all the way and see how this goes. So now I drew this structure using these structures. I made them up using ChemDraw. Now I try to show you something very interesting. If you look at these two now, look at this. This is the central atom here. This is the central atom. No, let me see it. Let me just mark asterisk. Central. These are all the central atoms. If you look at this one now in the 3-dimensional, this is attached to 4 stuffs. So the electron pair geometry of this is going to be tetrahedral. This is attached to 4 stuffs. Now remember, this one is attached to carbon. This is carbon attached to hydrogen, 4 hydrogen. Now this is nitrogen attached to 3 hydrogens and 1 lone pair. There are 4 attachments here. Here too, this is oxygen attached to 2 hydrogen and 2 lone pair. There are 4 attachments. The electron geometry of this molecule is going to be the same thing, but the molecular geometry will all be different. That's exactly what this is telling us. So assuming I want to draw the true dimension of how it looks like, if I'm not going to look, this is going to look this way. So this is carbon here. Okay, I'm going to use my usual red. I like using the red to draw. So this is going to be this way. So now this is going to be C, hydrogen this way. Now this bond is pointing away from me, and then this one is coming close to me. I'll put it this way, and this one is pointing this way. So this is going to be hydrogen. And again, this one will be, okay, I should have drawn this. Okay, I should have drawn this and close to this so that it doesn't have to take a lot of my space. I'm going to do that. Okay. Okay, so I'm going to draw this. I'm going to draw this here. So I'm going to say this is hydrogen. Now, this bond is pointing away from it. Remember, this is going to the board. I can't see it because this is a 3-dimensional molecule. It has 4 attachments. I'm going to put this one that is, the hydrogen is coming to me, and this one is pointed away to the plane, to the right. I can see. Now, this will be, now this is nitrogen. Now, if you look at this, remember, this has a lone pair. So what that simply means is that nitrogen has 1 lone pair here. So that lone pair, I'm going to represent it as an attachment. Remember, this is a lone pair. Well, if you don't want, you can use dots to represent the lone pair. So let's see. So I'm going to say this is a lone pair. Let me not use dash now. I'm going to use dash much later. And then it has hydrogen. Now, okay, this one is pointing away from me. And this one is pointing towards me. And this is pointing to my right side. This has 3 attachments, but it has what? Look at this. It has 1 lone pair. Again, this one, this is oxygen. In this oxygen has 2 lone pairs here. And then, so this lone pair, let me just use a balloon around it. So if you look at these 3 things, they have total of 4 attachments in them. Let's see. What is the EPG electron geometry now will be tetrahedral, because there are 4 attachments. All of them are going to be tetrahedral. Tetrahedral. This is also tetrahedral, 4 attachment. This is also going to be tetrahedral. Now, but because this one has no lone pair, now let's go back. When there are 4 attachments, if there are 4 attachments and there are no lone pair, the electron geometry is the same thing as the molecular geometry, the 3D. So it's going to be the same tetrahedral. So this is going to remain a tetrahedral shape. Now, what happens when there are 4 attachments, total of 4 attachments, and 1 lone pair? Look at it. It's tetrahedral here, but this is going to change to trigonal pyramid. This becomes, and if you look at it, looks like a pyramid. This is going to be trigonal pyramid. And finally, if there are 4 attachments, 2 lone pairs and 2 atoms, that's exactly what we have there. There are 2 hydrogen atoms, so this is going to give us what? Bent. Remember, this is what we have here. This becomes bent or V-shaped. So what am I trying to say with this is that it is only when the central atom has a lone pair that the EPG name changes from the molecular geometry name. Only when there's a lone pair. If there's no lone pair, like we see here, they remain the same. Let's quickly go to our problems immediately. Problem 1. It says, draw the Lewis structure of the following and use the VSEPR model to determine the electron pair geometry, the molecular geometry, and the bond angles. You need to memorize this stuff. So the first thing we need to do is to draw the Lewis structure. To draw the Lewis structure, remember as usual, you're going to calculate the total what? You're going to calculate the total valence electron. Carbon is in group 4 plus 2. Oxygen is in group 6. There are 2 atoms. If you add everything here, it's going to give you 16 valence electron. So if you draw this, remember carbon is always at the center. So we're going to have carbon is going to be, we've drawn some of this thing before, but I'm going to just do the first few. And the rest, I'm going to be a little bit faster with them. But first, now, there are 2 atoms here. We've used how many? We've used 2. So what are we going to do? We're going to try to satisfy this one. So let's see. If we satisfy this one, this gives us 8 plus 8, 16. But we have used all our electron, but carbon is not satisfied. What do? We begin to methodically clean out some of these guys. So I'm going to try to remove this and share this bond between these 2. Again, carbon still has 6, is not yet satisfied. I'm going to clean out this one again, remember that, and share that bond between these 2. And now this is the exact Lewis structure of this molecule. But the question says, we're not looking for it. It says, what is the EPG? Now, the EPG name, remember, in this case, let's try to count. When there is a central atom attached to 2 stuff, remember the double bond doesn't count. There are 2 oxygen atoms attached on both sides. And if you look at this table again, when there's no lone pair there, and there are 2 things attached, it's going to be linear. And then, since there's no lone pair, the molecular geometry is also going to be linear. So what are we going to do? Quickly we do that. So the EPG name is going to be the same thing. So this means that it becomes a linear molecule. The EPG tells us that it is a linear molecule. And then since it's a linear molecule, what is the molecular geometry? There's no lone pair. The molecular geometry is going to be the same thing as the EPG because there's no lone pair. And remember, these bonds doesn't matter. It has to count as 1. And however, when you're drawing the molecular geometry, you do not need to show the atom, you do not need to show the lone pairs on the peripheral atoms because it is not based on them. It is only based on the central atom. Since it's the same thing, we're going to also put what again here? Linear. And then what is the bond angle? The bond angle in this case is going to be 180 degrees when there are 2 attachments. So we go back there. It's going to give us 180 degrees. And that is how we do these problems. Now let's do GeBr4. Again, germanium is in group 4. You're going to look at your periodic table. Bromine is in group 7. And there are 7 of them, 4 times 7. If you add this to 4 times 7, it's going to be 28 plus 2. It's going to be 32 valence electrons. That's what we have here. Now, in this case, Ge is going to be the central atom. If you add a bromine here, it's going to be 4 bromine atoms attached. We have 32 to go. So, we've used only 4. So, we have many. Let's satisfy this guy. This one will be satisfied by this way. This will be satisfied. This will be satisfied. This will be satisfied. Let's count. This is 8 times 4, 32. And we've used our electrons. And let's see, this is all. And germanium has 8, so it is satisfied as well. So we're good to go. Now, if you look at this, germanium is attached to 4 stuff. So what that simply means is that the electron pair geometry here gives us what? The EPG simply gives us that this is a tetrahedral molecule because there are 4 things attached to it. However, because it's 4 things attached to it, the molecular geometry name is going to change. No, the molecular geometry shape will look differently in 2D, but the name is not going to change because there are no lone pairs attached to it. So I have tried to tell students to try to always draw those 3-dimensional shape. If there are 4 things attached, put this one on top. Now, put this one that is pointing away from you here. This one is pointing towards you, coming towards you that you can see. And this one is pointing to the plane to the right. So, of course, the EPG, the MG is not going to change. It will remain what? It will remain tetrahedral because there are no lone pairs attached to it. And finally, the bond angle here is going to be 109.5 degrees. And you're going to find that out here. There are 4 things attached to it. So the name of this is quantum of this. And this is exactly what we have here. A good example is what I have in there. So the next problem, problem 2, the same thing we're going to do. We're going to look at NH3. In NH3, again, we're going to start again. So in drawing this, I'm going to just draw what it looks like immediately in Lewis structure. And then you're going to figure out. So if you draw the Lewis structure, don't assume you know what the structure looks like. I'm just going to draw what it will look like in 2 dimensions. So if I'm going to draw the 2-dimensional structure, it's going to look this way. As H, 3 things attached to it. And if you do it well, it's going to have a lone pair. This is ammonia. It's going to have a lone pair. Now, because it has 1 lone pair, what it means is that, now, this tells you that there are a total of 4 things attached to this molecule, because this is 1 attachment, 2, 3, and 4. So the electron pair geometry, EPG, is going to, of course, be a tetrahedral molecule, tetrahedral. However, because of this lone pair attached to it, let's go back and look at that table. The table, you need to memorize it. When there are 4 attachments and one of them is a lone pair, it is tetrahedral. What is this going to be? The electron geometry is going to be what? The molecular geometry will be trigonal pyramid. So that molecule is going to be a trigonal pyramid. So if you're going to draw a trigonal pyramid, remember there's a lone pair here that is pushing it down, bending the bond. So this one, okay. So one of the bond, of course, is pointing away from me, then this is pointing towards me, and another one is going to my right. So this becomes a structure. So this shape becomes the molecular geometry. So the molecular geometry of this molecule will be a trigonal pyramid. Trigonal pyramid. A trigonal pyramid. And of course, the bond angle, what is it going to be? The bond angle is going to give us 109.5 degrees, and that's what bond angle is going to be. Again, we go to this one. Again, if you count the number of valence electron here, this will be 4 plus oxygen. Hydrogen is 1, carbon is 4, hydrogen is 1, so 2 times 1 plus oxygen is 6. This will give you 12 valence electron. If you draw this way, carbon is always at the center, so we're going to have carbon attached to oxygen, attached to hydrogen, attached to hydrogen. Hydrogen can't accept anything more, so you have to deal with this. So if you try to satisfy this, you have 2, 4, 6, 8, 10, 12. The carbon is not satisfied. What do we do again? Remember, I'm going to take away this one and make what? A double bond. If you make this bond now, it becomes complete. So, and there is no lone pair. What it means is that the 3-dimensional nature is going to be exactly the same thing, because there's no lone pair at all. So what that means simply means is that the EPG, electron pair geometry name of this guy, is going to be 3 things attached. If you look at that table, this is going to be what we call the trigonal planar. Because there's no lone pair, the molecular geometry will remain the same. Will remain a trigonal planar. And the bond angle, you look at it, it's going to be 120 degrees. We can look at that. This is a good example. No lone pair, there are 3 things attached, no lone pair. It's going to be a trigonal planar, and the bond angle is going to be 120 degrees. So it's going to be 120 degrees. And these are things you need to memorize to be successful in this class. We go to the next one, OF2. Now we're still going to draw the Lewis structure and figure out the EPG, the MG, and the BA, the bond angle. Again, I'm not going to go through drawing the Lewis structure. I'm just going to go straight to what the structure looks. So if you draw the Lewis structure correctly, it's going to look this way. O will be connected to F to F. Then remember, the peripheral atoms will always be satisfied. You're going to have something like this. And then because you see there are two things attached here to this guy, two atoms attached and two lone pairs. That's going to assume a different shape in there. The three-dimensional structure is going to be this way. It's going to be a bent structure. And if that happens, what it simply means is that this is the EPG. So the EPG, the electron pair geometry or the electron geometry, has four attachments. Four things attached to this guy. It is tetrahedral. And then the molecular geometry, which is this one, is going to be a bent structure. A bent structure is going to be bent. And then the bond angle, any tetrahedral structure, remember the bond angle is based on the electron pair geometry, is going to be 109.5 degrees. Again, we do this problem. In doing this problem again, you see this NO2 minus, we did this earlier in Lewis structure. This molecule can form two equivalent resonant Lewis structure. So we're just going to choose one of them. So if you draw this correctly, it's going to give you nitrogen is going to be at the center, oxygen is going to be this way and this way. And then if you draw it correctly, one of the double bond is going to be this way. This is what you get. And in fact, because this is an ion, you're going to have it this way. Now, this is what you get. If you look at this molecule now, this has how many attachments? Remember, we're going to count this as 1. So you're going to count this as 1, 2, and 3 attachments. So if assuming I want to put usually sometimes the test student can always put this to show that the lone pair is an attachment. That helps a lot. So there are 3 things attached to this molecule. Since there are 3 things attached to this molecule, what does that mean? It simply means that it's going to bend it again. That this molecule is just going to bend this to this way. That's what it means. So what it simply means is that the electron pair geometry or the electron geometry is going to give us, since there are a total of 1, 2, 3 stuff here, it's going to be a trigonal, planar, and then the molecular geometry is going to be bent. And then again, the bond angle, because there are 3 things attached to this molecule, the bond angle is going to give us 120 degrees. And that is how we do this problem. We go to the next one. Now, see, again, the same question. We should draw the Lewis structure, figure out the electron pair geometry, the molecular geometry, and the bond angle of each of these molecules. Now, if we draw the Lewis structure of these, which we did earlier, we're going to get something like this. I'm just going to draw it first. We've talked about how to draw the Lewis structure. This is just how to figure out the molecular geometry. We're going to draw something like this. Now, in this kind of, that's a mistake. In this kind of molecules, now it can have, you see, look at this now. This has two central atoms. So I have to specify. In exam, I'm going to say, specify this around. Is look at that. Wait. It says specify this around the carbon. So carbon is the central atom. Because I can use both oxygen or carbon, any of them as. I can use any of them. But in this case, I want it. So if you look at this carbon, how many things are attached to it? Let's see. How many things attached to this will now be 1, 2, 3, 4. Therefore, the electron pair geometry is going to be, this is going to be the same thing with the other one. So this will be a tetrahedral structure. So assuming I want to still draw the other one, it's just going to look exactly the same thing. It's not going to change. You can just exactly draw the same thing. And what it simply means is that the electron pair geometry is going to be tetrahedral. There are 4 things attached to it. The molecular geometry, because there's no lone pair here in this carbon, is going to still be tetrahedral. And then finally, the bond angle is based upon the tetrahedral nature. The electron pair geometry is going to be 109.5 degrees. That is how you draw this. Now let's look at this one, AS minus. Again, if you draw this one very well, if you draw this structure very well, you're going to get AS will be the central atom. You're going to get iodine as the attached. Remember again, before you watch this video, try to watch the video on Lewis structure and review how to draw the Lewis structure before you start watching this video. That will help you a lot. Now, if you draw, this is arsenic triiodide. If you draw it well, it's going to look this way. What it means is that there are 4 things attached to this central atom. And because of that, the EPG is going to be tetrahedral. However, the lone pair is going to change the electron pair geometry name to a different molecular geometry name, and that is going to be a trigonal pyramid. So if you draw what the new molecular geometry is going to be, you're going to have something like this. Again, in drawing the molecular geometry name, you need not specify the lone pairs around the peripheral atoms. You don't have to do that. It's not necessary. So again, if I'm going to say what is the EPG, because there are 4 things attached, again, if you want, let me count. Let's count. This is 1, 2, 3, and 4. This is going to give us tetrahedral. Then the molecular geometry, the Mg is going to give you what? It's going to, because this is different now from this is going to give you trigonal pyramid. You have to memorize those by practice. And finally, the bond angle is going to, because the bond angle is based on the EPG. The EPG is tetrahedral. The bond angle is going to give us 109.5 degrees. So you can pause this video at this point. Try to do this once yourself. And finally get back to them and finish them. I'm going to give you like 30 seconds and come back and finish it up. And the best way, like I said in my lecture, I have a lot of problems. The best way for students to understand these problems, the classes, or to understand the concept, the topic, is to practice as much problems as possible, and including the ones I have in the worksheet. Okay, let's take it off immediately. Now, this is hydrocyanic acid, or hydrogen cyanide. If we draw the Lewis structure of this, it's going to give us something like this. Remember, I'm just drawing it already because I know we've covered this topic. Now, if you look at this now, carbon is the central. So what it means, we have how many things? 2 stuffs attached to it. It doesn't, the triple bond doesn't matter. If there are 2 stuff attached to it, it's going to give us, that means the 3-dimensional shape will remain the same. It's going to give us this. So what it simply means is that there are 2 things attached to it, and there's no lone pair around the carbon. So we're going to say that the electron pair geometry, of course, is still going to be a linear molecule, because there are 2 things attached to it. And then the molecular geometry is going to be the same because there are no lone pairs attached. And the bond angle for any linear molecule, of course, the bond angle means, if you look at this, this makes sense. This is going to give you 180 degrees. And the last but not the least will be sulfur trioxide. What is it going to be? In trying to draw this again, this will have an equivalent Lewis structure, that's the resonance structures, but you just need to take one. So let's see. If you draw this thing very well, the correct Lewis structure of this molecule will be sulfur will be connected to oxygen. Remember, sulfur will be the central atom in this case. And there are no lone pairs here. So if you count any of this, just make sure you always draw the correct Lewis structure, count the atoms and make sure they satisfy the octet. And then from there, you begin to apply the knowledge of the VSEPR model to do the rest. So if you look at it, there's no lone pair. What it means is that this is also going to look, the electron geometry is going to look the same. So this becomes, the EPG will be 3 things attached to this. There are 3 things here attached. 1, 2, and 3. This will be a trigonal pyramid. No, trigonal planar, sorry. Trigonal planar. And then, finally, if you now put this, Now, because there's no lone pair, this is technically going to be exactly the same. It's not going to change because the lone pair is not there. So what that means now is that if we're going to write the electron pair geometry, it's going to give us three things attached all the time. It's still going to give you, oh, I can write it here. I can write the the molecular geometry, sorry. So the molecular geometry will still give you a trigonal planar. It didn't change. And the bond angle, of course, is going to give 120 degrees according to that table. So the best way to know and understand this stuff is to practice these problems as much as you can, and that is how you start getting some of those particular names and the bond angles into your head and understanding it far much better. And this is the last problem. We're going to stop at this point. Again, if you have any questions, do not forget to send me emails or talk to me through other channels that we can communicate. And if you also want to stop by, you are free to stop by anytime and talk to me. Thank you once again for listening, and enjoy the rest of your day. Bye.